Okay, here we've got question 1. So we've got a triangle, it's pinned at A and it's got a roller joint at C. So we know we're going to get two reactions at A. So we'll get a vertical, we'll call that AY, and we'll get a horizontal, we'll call that AX. And because C is at a roller, it can only support a vertical load, so we'll call that CY. The first thing to do with any framework then is to calculate the reactions at A and C, and then we'll move on to method of joints to calculate out the internal loads in each of the members. And I notice here we've got a load of 500 newtons at 45 degrees. So one thing that I would do with that generally is I'll split that into its horizontal and vertical components. So that is actually made up of those. And if we take that 500, so if we've got 500 as our hypotenuse, and that's made up of our horizontal and vertical, then we could say then if we call this X and Y, we've got 45 degrees. So we could say, well, the X force, for instance, equals 500, and that will be cos 45, which I think equals, rounded up, 353 newtons. And that will be also the same for the vertical direction. Okay, so let's try and work out what our reactions are at A and C. So I'll draw those on again as I had on the last diagram. So we call that AY, and I put this one on as AX, and also CY. Right, if I take moments then about point A, if we look at point A, imagine putting a pin in at point A there, then the 500 newtons that we've got here, you can see that if you pushed on at point B, that would tend to rotate the whole framework around point A in a clockwise rotation. What stops it doing that would be the vertical reaction there at C, pushing back in an anti-clockwise direction. So let's take moments about A then, and that should be able to enable us to find the vertical reaction at C. So the sum of the moments at A, we know it's got to be 0 if it's in equilibrium, it's not going anywhere. So what have we got then? Well, remember we've resolved this 500 newtons into two components. We've got the 353 horizontal, and we can resolve that to 353 vertical as well. So we've got 353 newtons there pushing horizontally, so from kind of left to right, and its perpendicular distance is 2 meters. So we've got 353 times by 2 meters. And what stops that? What else have we got? We've got the reaction CY at 2 meters, and the way that the arrow is indicating there would cause the framework to rotate anti-clockwise, so it's positive. The first one was negative, CY is going to be positive, plus CY multiplied by 2 meters. So we can see then that the vertical reaction at CY is going to equal 353 newtons. And we can also use our other two equilibrium equations, so we can look at the sum of the forces in the X direction, for instance. So let's do that. What forces do we have in the X direction? Then we've got this 353 newtons pushing from left to right, so that's going to be positive. So we've got 353. And the way that I've drawn it on the diagram here, look, we've got AX pulling to the left, so that's going to be minus AX. So therefore, AX is going to equal 353 newtons as well. And then finally, let's do our vertical direction. We've got some of the forces in the Y direction equals 0. So what have we got? Well, we know that CY is 353. So we've got 3 53. And we've also got the vertical component of the 500 newtons, and that's also pushing upwards. So that's plus another 353. And the way that I've drawn the diagram here, AY is also going upwards. So I'm going to put that as a plus AY, and that all equals to 0. So therefore, if I take the two 353s to the other side, I get AY equals minus, and double that is 707 newtons. So this negative here and the AY direction means that the arrow is the wrong way round on my diagram. So when I come to do my method of joints, I'll make sure that my arrow AY is pointing downwards. So now we'll start to look at each individual joint. We'll draw the free body diagram and resolve the forces at each one of those joints. And I'm probably going to start at joint A because I've got the members of the framework lined up with the two reactions, so it should be a straight like for like in terms of the forces. So we'll do that on the next slide. Okay, so looking at joint A, then let's draw what we've got. So we'll draw a quick free body diagram, and that should put everything in place for us. So if I draw the diagram, there's the joint. Remember the AY was pulling down, and that was 707 newtons. We know that AX was pulling to the left, and that was 353. And I've got the two members there of the framework, and just by inspection then, I'm going to put the arrow on there, assuming that both of these are tension. So you remember, if the arrow is pulling away from a joint, it's in tension. You can imagine yourself if you cut through. So imagine if I cut through AC, I would have to pull away from the joint at each end if it was in tension. So I'd have to pull away from A and pull away from C. So here then, if I sum up the forces in the X equals 0, I've got 353. I'm going to call this force AC. This one is AB. So that's minus 353, it's pulling to the left, plus AC. So therefore, AC equals 353. It's a positive number, it means my arrow was right. So it's 350 newtons, and I'm just going to put there for tension. Then I can also do the sum of the Y direction equals 0, which equals, I've got 707 pulling down, so it's minus 707. AB is pointing up, so plus AB. Therefore, AB equals 707. It's a positive number, so that also means the arrow's in the right direction and it's in tension. So the only force we don't know now is the internal force in BC. So I could pick either joint B or joint C to calculate this. I'll pick joint C because the load is vertical. I don't have to resolve it into the components, so I'm going to go joint C, but it doesn't really matter which one you use. Then what have we got here? Well, we know that the reaction is 353 pointing upwards. We now know that AC is in tension, so we have AC, the force in AC there is in tension, and it was 353 newtons, and here we've got the force in BC, and I'm going to draw the arrow as if it's in compression, so it's pointing to the joint, just because I think that will resolve the forces either in the vertical or the horizontal. It doesn't really matter which one I pick. Let's pick the X direction. It will work with both. If you pick the X or the Y direction, you'll end up with the same result. And in the x direction, I've got 353, and that's negative because it's pulling to the left. And that's going to be plus, and it's going to be if we can imagine, BC is made up of two components, again like that. I'm going to resolve this into the horizontal component. So I know the angle is 45 degrees, so it'll be the adjacent, so it'll be cos 45, so it'll be BC cos 45. Therefore BC equals 353 over cos 45, which equals 500 newtons. I ended up with a positive result, so my arrow was correct, and I'd assume that was in compression, 500 newtons in compression. Question 2 here. Looks a lot more complicated than the first question we've just looked at, but in essence we do exactly the same procedures we did before. So we'll try and find the external reactions, and then once we've got those, we'll pick a joint and then go through from one joint to the next, calculating the internal reactions. So if we look at this, we've got a pin joint at C, so joint C can support two loads, so I'm going to kind of assume CX pulls to the right there, and I'm going to assume CY is going vertically. And then at point D, it's on a roller, and this time the roller is vertical, look, so all it can do is support a load at 90 degrees to that roller as if it's rolling on a surface, and that'll be dx. And looking at this again, a good place to start is to take moments, and if I take moments at C here, then the only force that prevents any rotation is the reaction at D there, the dx. So if we look at this, we've got 200 newtons, so that's going to try and turn the whole framework clockwise, anti-clockwise about C, and also we've got this 300 newtons here, which is also going to try and turn it anti-clockwise about point C. And what's going to stop that then is point D, and that's going to try and turn it clockwise to resist that. So the first thing we'll do is we'll take moments about C, which should give us the force in D, and then we can resolve the horizontal and vertical forces to find out the reactions at C. Right, taking moments, so if we take moments at C, they've got to equal 0, haven't they? And what have we got? Well, if we look here, we've got 300 newtons, and that's multiplied by 2 meters. So we've got 300 multiplied by 2, and that's going anti-clockwise, so I'm going to call that positive. And then I've got 200 newtons, and its perpendicular distance from C is 1 meter. So that's also turning it anti-clockwise, so it's positive. So I've got 200 times by 1, and what's preventing that then is this horizontal reaction at C. So I've got minus, not C, sorry, D. dx, and its perpendicular distance is 2.5 meters from C. So if we rearrange that, we've got dx, take it over the other side, equals 2 times by 300 is 600, plus 1 times 200 is 200, so that's going to be 800, isn't it? All divided by 2.5 meters, so 800 divided by 2.5, that gives me 320 newtons. End up with a positive result, so my arrow, which I put on the diagram on the previous slide, was pointing to the left, so it's in the right direction. Okay, from there we can go on to resolve the forces. Let's look in the x direction. So externally we now know that the reaction at D is minus 320 newtons because it's pushing to the left, and I don't know whether you can see it on here. Oh, and then I put my arrows for C in those two directions, so it's going to be plus Cx, so therefore Cx equals also 320 newtons, and that's going to be pulling to the right. Let's take the sum of the vertical. We've got in the vertical we have minus 200, so we've got minus 200, and we've got the minus 300, both those pointing down, and the only other thing is plus Cy. So therefore we've got 500, so Cy equals 500 newtons, and that's pushing upwards. Next thing we have to do then is pick a joint to try and calculate the internal forces in the members. So we can pick any of these joints. Some will be easy to solve, some we might not be able to solve with the information we've got at the moment. And again, I think if we look at joint C, we've got reaction forces just in the horizontal and vertical, and we've only got two members in the horizontal and vertical, so they should balance out as well. So the obvious place for me to start would be at joint C. So we'll do that on the next slide. At joint C then, draw out the free body diagram. We know that we've got 320 newtons pulling away to the right, and I'm going to draw the reaction force above the joint here. So we've got the vertical reaction force of 500 newtons, and then we've got the two members, we've got BC and DC. So we've got BC and we've got DC, and I'm going to draw them. Hopefully it's fairly obvious that you need to draw them like that, and hopefully now it should be fairly obvious. We could just say therefore, well, now let's do the calculation just for completeness, at least for the first one. Then we could say the sum of the horizontal in the x direction is 320 because it's pulling to the right, BC is pulling to the left, so it's minus BC equals 0, therefore BC equals 320. It's pulling away from the joint, so it's in tension, and also therefore we can say that DC equals 500 newtons in tension as well. Let's move on to another joint then, and probably looking at it, if we look at joint D, then we've got the horizontal reaction force, we've got the force in DC, so we should be able to, and because DC is vertical, it can't support any horizontal load, so therefore we could probably work out what the forces are in the other two members there. So let's look at joint D. Draw it out. We know we've got the reaction up from the wall, which was 320 newtons. We know we've got the force in DC, which is 500 newtons, and then we've got the force in AD and the force in BD. Now on this one, it's not quite so straightforward as to which way these forces are going to balance out. So I'm going to hazard a guess for BD and say that's in compression, because the vertical component of BD must match the vertical component there of 500. And AD, I'm not too sure how that's going to balance out, so I'm going to assume it's in tension. If I get a positive result, I know that my direction was right. If it comes out negative, then obviously it was wrong. So let's first of all, if we look at this, we'd need to work out the vertical first, because in the horizontal direction, then we've got two unknowns at the moment. We've got the horizontal component here of BD plus the horizontal AD, so we couldn't work out the difference between those. But in the vertical direction, there's only two forces, one which is the force in DC, which is 500 newtons, and that has to be balanced out by the force in BD, or the vertical component. So if we look at that, we've got 500 and it's going up, so we've got 500, and the way I've drawn BD, it's down, so it's minus BD, and it's going to be sine, because it's a sine component of this angle here. So we need to work out what that angle is in what theta is, and in order to do that, let me just do that as a little aside. Where shall I do that? Just about here. So here we've got, if I draw that triangle out to work out what theta is, we've got 1 meter and we've got 2.5 meters. So this angle theta equals the inverse tan of 2.5 over 1, which equals, hold on, 2.5 68.2 degrees. So here we have, oops, sine, kind of messed it up a bit here, 68.2. So therefore BD equals 500 over sine 68.2, which equals, by my reckoning, 538 newtons. And again, I've got a positive result there, so that means that my assumption is in compression is right. Now we should be able to do the x direction. So if we look at the x direction, equals 0. So what have we got in the x direction? We've got minus 320, and we've got plus, and we now know what BD, so that we're looking at the horizontal component of BD. BD is 538, so we've got plus 538, and that'll be cos 68.2, and the way I've drawn AD, which will be minus AD. So therefore AD is going to equal minus 320 and minus 320, and that's going to be plus and 538 multiplied by cos 68 I think is 200, so it's going to be 200. Therefore AD is going to equal minus 120. So that means that my arrow on here was wrong. So this was the wrong direction. AD is actually pushing in, is in tension. So, sorry, not tension, is in compression, not tension. So AD equals 120 newtons compression. The only unknown that we have now then is the internal force in AB. So let's pick a joint. Let's pick joint A and see if we can work out what that load in there is. So let's draw the free body diagram. We've got 300 newtons applied. We've got a compressive load in AD, which we just worked out to be 120 newtons. And I'm going to draw the arrow that way round for AB, which means it should balance out both of these. So we could pick the X or the Y. So let's pick the X equals 0. Then we know that this angle in here is the same as the other side, so that's going to be 68.2 degrees. So we've got summing the X equals, well, we've got minus 120 plus AB, and it's going to be cos 68.2. So AB equals 120 over cos 68.2, which by my reckoning equals 323 newtons, and I get a positive result, so it's in tension. We could do that also by looking in the Y directions. We should get the same answer. If we look in the Y, we have minus 300 plus AB, and that's sine 68.2. AB is going to equal 300 over sine 68.2, which again should give you 323 newtons tension. So if you want to, just double check those values on your calculator, make sure that you get the same value for both of those. And that's all of the internal forces in the members found for question 2. Question 3 then, we've got two forces applied, and in this case you notice we've got two pin joints on here, so we could end up with, theoretically we could end up with 4 reactions. We could end up with, if it's pinned, theoretically we could have something like this for C, and similar at D. And you might think then it's going to be difficult to calculate what the reactions are with having 4 of them, but if we notice, if we look at point C, remember, because these are assumed as frictionless pin joints, then the forces within the members can only be directed along the axis of the member. And if there's only one member there at joint C, it can only support a load in that direction, which in this case is a horizontal direction. So therefore, at point C, it can't support any vertical load. Any vertical load applied there would just cause it to rotate. So in fact, we've only really got 3 unknowns. So that's going to help us before we start. And another thing which I'll do is also highlight, we've got 500 newtons, and I know that at 53.1, that makes a 3, 4, 5 triangle. So if we've got 5 there, we have 4 there and 3 there. So effectively we've got 500 newtons, and we can split that up into 400 newtons vertically and 300 newtons horizontally. And that'll help us with the calculations around the joints. So first off, I think what I'll do is the usual. I'll take moments about one of the reactions, and in this case, if I take it about point D, I've only got one unknown force, which will be the horizontal at C. Once I've got that, I can resolve for the X and Y to find out the reactions at D, and then move on to method of joints as we've done before. Looking at taking moments then about joint D. So we've got the sum of our moments at D equals 0. And what do we have then? Then we have C multiplied by 4 meters. And let me just put these on here, and I'm going to put C pointing that way, and I'm going to assume this goes that way and that way. And we can split this 500 here into a 400 load that way and a 300 load that way. So at point, taking moments at D, we've got C multiplied by 4, and we've got this 400 newtons and the perpendicular distance for that, so that's going to be 3 meters, isn't it? And it's going to be turning it anti-clockwise, so that will be positive, so it's plus 400, and that's going to be multiplied by 3. And we've also got this 400 here multiplied by 6, also turning it anti-clockwise, so it's positive. And the way that I've drawn C, let's look at that, as turning it, if I imagine pulling to the right at point C, it would turn the whole thing round in a clockwise direction, so that's going to be negative, so I need to put that, in there. So my reaction then at C is going to equal, well, we've got 3 times by 400, so that's going to be 1200. 4 times by 6, or 400 times by 6 is going to be 2400, divided by the distance to C, which was 4. So that's 36, so that's going to be 900 newtons. Okay, and if we consider then the sum in the x direction, we've got the 900 that we've just calculated for C, and that came out positive, so it's pulling to the right. And we've got the horizontal component of this 500 newtons there at point A, so that's also going to be positive, plus 300 then, and minus dx, so therefore dx then is going to be 1200 newtons, and that's in the direction I've shown it, which is pushing to the left, which, if you think about it, makes sense of how the system would be loaded. Let's look in the y directions then. We've got, so that's going to equal 0, minus 400, minus another 400, and plus dy, so therefore dy is going to be 800 newtons, and that's pushing upwards. Looking at our joints then, method of joints, I think if we look at joint C, that's pretty straightforward to resolve. So let's if we draw the free body diagram, we know that our reaction on the wall was 900 newtons, wasn't it? And the only thing occurring at joint C is the force in BC. And I've drawn it in tension there, pulling away from the joint because it's got to balance the 900. So therefore, we can easily say BC equals 900 newtons tension. We've got 2 reactions and 2 unknowns at joint D, so that's probably not a bad place to look next. So let's draw that out. I know that I had 1200 I'd calculated, and the vertical reaction was 800. And let's draw these. We've got here the loading AD and the loading BD. So I'm going to draw that way because I know that the vertical component has to be 800, and I'm going to draw AD that way as well. if I'm wrong, then in fact, now let's stick with the convention. If I don't really know, I'll get the eraser to work. If I don't know, I should really assume that it's in tension. So let's assume it's in tension. And let's resolve the vertical component to find BD. So what have we got? We've got 800 and we've got minus BD sine, and again here this angle I know is 53.1 because it's a 3, 4, 5 triangle, just like we've applied the load, so that's going to be 53.1. Therefore BD 800 over sine 53.1, which equals 1000 newtons, and the way that I've drawn it, it's in compression. If we look in the x direction, we have minus 1200 plus BD is 1000, and it's going to be the horizontal component, so that's going to be cos 53.1, and it's going to be minus AD, the way that I've drawn it on there. So AD is going to equal 1200, oops, and this here becomes 1000 cos 53.1, I think is 600 newtons, so that's going to be minus 600, whoops, looks like goo, equals minus AD. Therefore AD equals minus 600. So AD is going to equal 600 newtons, and that's going to be compression because I got the sign the wrong way around. We just need to find the joint, the load in AB now. So we could pick a joint that involves AB. Let's pick joint A. Draw the free body diagram. We've got 600 compression in AD. We've got, well, let me draw them in red. I've got them resolved, haven't I? I've got that resolved into these two forces, which is 300 and 400. That's my 500 load resolved into its components, and I've got the load in AB. So really then we know that the vertical component of AB equals 400 newtons. So if we look in the vertical direction, then we have minus 400 plus AB sine 53.1, therefore AB equals 400 over sine 53.1, which should give me, I think, 500 newtons tension. We could also have looked in the horizontal direction there to find AB, so that would have been 300 minus 600 plus AB cos 53.1, which again should give you the 500 Newton tension. Or alternatively, we could have looked at joint B instead, so just to show that that would have worked as well, because we've got all the information we need at B. If we draw the diagram, we know we've calculated out 900 tension for BC. We have 1000 compression for BD. We have an applied load of 400 newtons, so that 400 is what was applied externally, and we've got AB. Remember, that's 53.1, the angle there. So we could look at that. We could look in the horizontal direction, perhaps fx equals 0. What have we got in the horizontal direction? We've got 900. We've got the horizontal component of this 1000, which will be cos, so that's going to be, and it's going to be a minus 1000 cos, and that angle again is 53.1, and it's also going to be minus AB cos 53.1. So therefore AB is going to equal this 1000 cos here equals 600, so we've got AB equals 900 minus 600 over cos of 53.1, which again you should find to be 500 newtons tension. And that fully solves the internal loads for question 3.